We finally got another video about vertex algebras. And in the last video, we looked at the basic construction of the Heisenberg algebra. And here we want to look at maybe a summary of that construction and some calculations. We're past the point where we can really appropriately review the full definition of a vertex algebra in every video, just for the constraints of time. And I'll be putting these videos out more frequently in the future. The eventual goal is to have a huge library of videos about vertex algebras coming from a pretty understandable point of view, in the future. Okay, so let's look at the basic idea of a vertex algebra before we jump into our examples for today. So we've got a vector space, and there are infinitely many products between two vectors, and those products are indexed by the integers. And so here we denote the mth multiplication or product between u and v by u sub m v. So we just put that m in the subscript. Another way of thinking about that is you're associating a linear map to u and this integer m. Okay, and then as we've talked about in previous videos, if m is negative, this is like a generalization of a commutative associative algebra. And if m is non-negative, this is a generalization of the Lie bracket. We'll see this like in our calculation today. Then furthermore, the associativity is connected to this expansion of the vertex operator. So if you take y of a sub n minus 1 bz, so that's the vertex operator associated to this vector, you get 1 over n factorial, and then the normally ordered product of the nth derivative of the vertex operator associated with a and b. So again, we did a whole video on the normally ordered product. I'll let you guys check that out if you need to. And then if you take a non-negative product of an with b and then expand its vertex operator, you get this object right here. So it's going to be the sum as k goes from 0 to n, this binomial coefficient n choose k minus z to the n minus k, and then this commutator of the kth mode of a, or the kth multiplication of a, with the whole vertex operator of b. So we did some basic calculations in an arbitrary vertex algebra for both of these types of things in previous videos if you guys want to check that out. So the too long didn't read of the Heisenberg vertex algebra, in other words, a summary of the calculation, goes like this. So we'll use this script uppercase H for a rank 1 Heisenberg algebra generated by a single vector alpha. And linearly, this Heisenberg algebra is isomorphic to a ring of polynomials with infinitely many variables. And we could call those infinitely many variables alpha minus 1, alpha minus 2, alpha minus 3, and so on and so forth. The vertex operator for our generator is denoted by alpha of z or y alpha z, and that's going to be the sum over all n and z of alpha n z to the minus n minus 1. The component operators commute like this. So this is like sort of a affine Lie algebra commutation relation if you built it off of an abelian Lie algebra. So we've got alpha n is m delta m plus n 0. So this is the Kronecker delta. It's 0 unless m plus n is equal to 0, and then it's 1. Then from this commutation relation of the component operators, along with this commutativity here, we see that if n is bigger than or equal to 0, then alpha minus n minus 1 acts as just multiplication by alpha minus n minus 1 in this polynomial ring. So if n is bigger than or equal to 0, then this minus n minus 1 is less than or equal to negative 1. So that would be like one of these negative multiplications, which is again a generalization of commutative associative algebra. Next, if you take alpha of n, so that would be like the nth product of alpha with some other vector, that acts as this partial derivative operator. So we've got n times the partial derivative with respect to alpha minus n. And so that's acting on something from this polynomial ring. So that's how we kind of think of this action. Okay, so now that we reviewed a little bit, I want to do two in-depth examples of calculations within the Heisenberg vertex algebra, and that's kind of the big goal for the video. So let's get rid of that and then we'll do that. So in our description, we saw how to multiply alpha to any object in the Heisenberg algebra, just kind of with any appropriate multiplication, be it a negative multiplication or a positive multiplication. But what if we've got some associativity built into that? And so this example will highlight this, and we'll be using these two formulas over here, or really just this top one. So we've got this vector alpha minus 2, alpha minus 1 on the vacuum, and we want to take the negative second multiplication of this vector with the vector alpha minus 4 on the vacuum. Okay, so we're going to use the definition of the vertex operator along with these expansions which follow from the definition of a vertex algebra. Okay, so this is going to be the coefficient of the first power of z of y of alpha minus 2, alpha minus 1 on the vacuum with z, and then that applied to alpha minus 4 on the vacuum. So let's recall that the first power of z is going to be attached to the negative second mode, or the negative second multiplication of this vector by the definition of the vertex operator. Okay, but now using this rule here, we can expand this vertex operator in terms of the normally ordered product. So this is going to be the coefficient of z to the first power. I won't write that first power anymore. And now we'll have inside of this the normally ordered product of the derivative of alpha of z. So that'll be from this alpha minus 2, and then just plain old alpha of z. So that comes from this alpha minus 1, and then we need to apply this to alpha minus 4, 1. Now we'll expand this normally ordered product out, and I want to point out that this is the derivative with respect to z. So when we expand this normally ordered product, we have to split this first field into two pieces, like all the negative components and all of the non-negative components. So let's get that written down real quick. So we'll have the coefficient of z, and then expanding out this normally ordered product, we'll have the sum for m less than 0 of minus m minus 1 alpha m z to the minus m minus 2. So that would be like the negative modes attached to this derivative. Notice I took the derivative of the vertex operator there. And then I have just this field by itself. So this is going to be the sum as n goes over all integers of alpha n and then z minus n minus 1. And then I have to reverse the order, but then take the positive modes instead of the negative modes. So let's do that. So that's going to give us plus this sum as n goes from the integers of alpha n z minus n minus 1 times the sum over non-negative m of the same kind of thing. So we've got minus m minus 1 and then alpha m z minus m minus 2. And all of this is still acting on our alpha minus 4 on the vacuum, like that. Okay, so just to reiterate what went on here. So here we thought of this as maybe our capital A field. This is like our capital B field. And by the definition of the vertex operator, this expands this thing into A minus B and then B A plus. Great, so again, that's by the definition of the normally ordered product. Okay, so now let's mash these two pairs of sums together and see what we get. Okay, so off the video, I pushed these two iterated sums into double sums. Now we want to take the appropriate coefficient, so that's going to be the coefficient when z is to the first power. But that means that in each of these, we need minus m minus n minus 3 to be equal to 1. So that'll allow us to solve for n in terms of m. Notice that that means that n is equal to minus m minus 4. So that tells us that we can get rid of all of the integers here and replace the n's with minus m minus 4. So let's do that here. Minus n minus m minus 4. And then the same thing here. This also is going to be minus m minus 4. And now I no longer need my z to the whatever power or my coefficient of z out front, because that is exactly what we've done. We've extracted that appropriate coefficient of z. Okay, so now that we've gotten this, let's bring this portion of the calculation to the top and then move on to the next step. Here we've got a cleaned up version of what we did on the last board where we extracted the appropriate coefficient. Now we want to use the fact that our positive multiplications with alpha are like derivatives and our negative multiplications are just like left multiplication by those appropriate terms from the polynomial algebra. So notice here we're summing over all non-negative values of m. So that means here we've got like alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and so on and so forth. But notice that this alpha m, since we're summing over all of the non-negative values, actually acts like m and then the partial derivative of alpha minus m. But look what's to the right of this. There's just an alpha to the minus, or alpha sub minus 4. So since there's just an alpha minus 4 there, it means that all of those partial derivatives will give us a 0 except for one special value, and that is if m is equal to 4. That'll be the only non-zero term from this sum. Now let's do a similar investigation over here. So here we're summing over all negative values of m. But notice if we plug in the first couple of negative values of m in here, we're okay. For m equals -1, we get that this is equal to -3. For m equals -2, this is equal to -2. Those are all okay. But then when m is equal to, let's see, -8, you get that this is equal to a +4, and you get that same kind of thing with the derivative there. So that opens up a couple of more possibilities for values of m here. So just to summarize that, the values of m that are allowed here will be -1, -2, -3, and -8. So -1, -2, and -3, because that leaves us with a negative number inside of this alpha, so it's just like multiplication. -8, because at that point it's become a partial derivative, but that partial derivative matches with what is to the right there. Okay, so now that we've got all of these values of m sorted out, we can expand this out. So let's see what we get. So for m equals -1 in this first sum, notice that's going to have this thing like just disappear. So that actually doesn't count at all. This is a allowed value of m, but that gives us 0 just because of that term right there. So that means we need to look at m equals -2. So that's going to give us, we'll put into there, that'll give us the number 1, and then alpha -2, alpha, well, let's see, that's going to be another -2, and then alpha -4 on the vacuum. So that'll be our m equals -2 term. Now let's look at m equals -3. Plugging that in here, we get a 2. And then we'll have alpha -3, alpha -1, alpha -4 on the vacuum. So again, that's our m equals -3 term. And then let's look at our m equals -8 term. So plugging in -8 to this, we'll get 7. So that'll be +7. And then we'll have alpha -8, alpha 4, alpha -4 on the vacuum. And then one last thing over here from this second sum, m equals 4. So plugging that into here, we'll get a -5. And then we'll have alpha, let's see, -8, alpha 4, and then alpha -4 on the vacuum. Great. But now we'll use the fact that alpha 4 acts as a partial derivative with respect to alpha -4 and a multiplication by 4. So that'll allow us to simplify this. These guys right here calculate or collapse just to the number 4, like that. And then we can start bringing everything down. So let's do it in like some sort of order. So notice here we'll have alpha -4, alpha -2, alpha minus 2 on the vacuum. That's the first term, plus 2, alpha minus 4, alpha minus 3, alpha minus 1 on the vacuum. That's the second term. 7 minus 5 is equal to 2 times 4 is equal to 8. So that'll leave us with a plus 8, alpha minus 8 on the vacuum. So notice what we ended up with is these three terms, and the index sum of all of these terms is equal to 8. Notice that minus 4 minus 2 is negative 8. Negative 8 is obviously negative 8. And then if you sum those, you also get negative 8. So this is all occurring at a weight of 8. Okay, so let's maybe get rid of this and we'll do one more calculation. Okay, we're gonna do one more calculation and maybe we'll run through this one a little bit more quickly. So let's say we've got the same two vectors. So we've got alpha minus 2, alpha minus 1 on the vacuum, and then we've got alpha minus 4 on the vacuum. But last time we took the negative second multiplication between them. Now we wanna take the first multiplication between them. So that means we need to take the coefficient of z to the minus 2 from the appropriate vertex operator. So let's recall that that's going to be the vertex operator y alpha minus 2, alpha minus 1 on the vacuum with z alpha minus 4 on the vacuum. Like that. Again, just because of how the vertex operator is defined, the negative second power of z is attached to the first multiplication. Okay, so now I'm going to skip a couple of steps that are essentially exactly the same as what we did on the last calculation. I'll just bring down this coefficient of z to the minus 2 and then jump to what our vertex operator looks like. So this is going to start off with the sum over all negative m and all integers n of minus m minus 1, and then alpha m, alpha n, and then alpha minus 4 on the vacuum. So that's like our first part, and then we'll have something like very similar for our second part. So this will be the sum over all non-negative m and all integers n of, again, minus m minus 1, alpha n, alpha m, and then alpha minus 4 on vacuum. Now, playing the same game that we did before, we can extract the appropriate coefficient. Oh, I should say here that all of this is attached to a z to the minus m minus n minus 3 again. So this is z minus m minus n minus 3. Great. So here we want to take the coefficient of z to the minus 2, which means we need to set minus m minus n minus 3 equal to minus 2. Then we can solve that for n, and we'll see that n is equal to minus m minus 1. So that means we can go in here and replace our n with minus m minus 1. So let's do that everywhere. Good. And then after doing that, we can get rid of our sum over the integers. We can get rid of our formal variable z and taking the coefficient, because we've essentially done that all in that step. Now, we want to notice here we're summing over all of the negative values of m. So if we plug in m equals minus 1, we'll get a 0 here. M equals minus 2, we'll get a 1 there, so on and so forth. All of those will give us 0, except when m is equal to negative 5, that'll make minus m minus 1 equal to 4. So just as we had seen before, we only get to keep a couple values of m. In this case, we just get to keep m equals 5. And then similarly over here, we just get to keep m is equal to 4. Oh, and I should say this should be m equals minus 5. So now let's see what we get. That means this is going to be equal to, well, plugging minus 5 into there, we get 4, and then alpha minus 5, and then alpha 4, alpha minus 4 on the vacuum. So that's what we get from this first portion. And then from the second portion, let's see what we get plugging 4 into here. We'll get minus 4 minus 1, so that's minus 5. And then we'll have alpha minus 5, alpha 4, alpha minus 4 on the vacuum. Now we do a similar calculation as before. This alpha 4, alpha minus 4 will just give us 4 because that's like a partial derivative with respect to alpha minus 4. So we'll have a 4 from that. Then this 4 minus 5 will give us -1 multiplied to this 4 will give us -4. So in the end, we'll have -4 alpha minus 5 on the vacuum. So that's what we get for this first multiplication. So notice it decreased the length of our object. Okay, so maybe I'll erase this and I'll give you guys a couple of problems that you might want to try for homework. So here are a couple of like pretty similar calculations that you could use to practice this technique if you wanted to. So let's say we combine the vectors alpha minus 3, alpha minus 2 in the vacuum. Then we want to take the negative first multiplication between the resulting vector and this alpha minus 3, alpha minus 1 with the vacuum. So that maybe be 1. Then we've got another similar one here where we take alpha minus 1 with the vacuum, and then the 0th multiplication with alpha minus 5. Then maybe like alpha minus 4, alpha minus 2, and the 3rd multiplication with alpha minus 2. And then finally, one that's a little bit tricky would be alpha minus 1, alpha minus 1, alpha minus 1 with the vacuum, the negative 2nd multiplication between that and alpha minus 1. So if you guys are psyched, you could work these out and post what you get in the comments. And that's a good place to stop.